You need to start over now.
Okay, so okay. I guess you all know this, this schematic. You know that air pollution is a problem, and particulate matter in particular. For Belgium, there are a little bit less than 9,000 anticipated premature death per year, and I think about 8,000 of them are due to particulate matter, and a little part also to NO2 or ozone. But it's mostly particulate matter, and you all know that the smaller the particles, the deeper they can go through the respiratory system. So we usually say that the smaller, the more dangerous. It may not be always the case because of their nature, of course, and also because depending on their size, they can be how do you say, deposited in different regions. So depending on you, it's not always the smaller the more dangerous. Okay, go ahead. So in the framework of PMLab, the goal was to have consistent PMX measurements. PMX X stands both for 10 and 2.5. And we noticed that all regions were measuring particulate matter, but all regions were measuring them with different instruments. So that doesn't mean that they are not working well, but that means that there could be differences between these measurements. So the first part of the project was to make them consistent and evaluate them against the reference method. And the reference method is still gravimetry. So we put a sampler on the field. We take the aerosol for 24 hours, and then it's collected on the filter. It moves to another part of the instrument, and then a new one comes, and so on for 2 weeks. And then we just go back to the lab and weigh the filters. So we typically weigh something about 1 milligram, something like that, and then we can retrieve the concentration. And once we have these reference measurements of particulate matter, we can compare them with the results from the optical method, or even different methods. The beta method, it uses a radioactive source, and it measures the attenuation of the signal through the material. And there are also microbalance that can really weigh the particulate matter live, but of course they are very sensitive because that's very low weights to weigh. So and once we had these samplers posted just against the cabin where they make the reference measurements, we could derive the calibration factors to have something that was as homogeneous as possible for the Dury rank. So that was 13 years ago. Now all states have to make this analysis from comparison of optical methods against the reference method every year, but also every 3 years to revise possibly the factors. But this is some routine works now. But it was not when PMLab was launched. So all these calibration equation is how much we have to multiply the optical value to get something as close as possible to the reference value. And you can see that they are very different from one side to the other one. It's because the equipments are different, but also the nature of the particles are very different from one side to the other. So that was for the measurement. And for the modeling, nowadays we mostly use chemistry transport models. So we use information about emission sources and the land use, the the topography and things like that, and we can make maps. These are the results that are available on CAMS, Copernicus for atmospheric modeling system, something like that. And these are the results that you can find on the ISSeP website in Belgium. So you can see that the resolution is not, it's not bad, but it's not a very fine resolution, and that's nowadays computation, because 13 years ago the resolution was more about 30 or 40 kilometers, so that was not that good. So what we decided to use in the framework of PMLab was the PMLab model. But the PMLab model is based on Rio, which was developed by Vito in Belgium. So the idea of this model is to take all the sites where there are measurements and to make a kriging, which is basically an interpolation. But before to make this interpolation, we're gonna detrend it. Detrend it because mathematically we have to, but also because depending on where you make your measurement, if it's a traffic site or if it's a rural background site, you will see the concentration levels that will be very different, and they go more or less according to this curve. So if here we have a very, let's say, a background reference, a rural background site, and here we have the traffic sites, and in between, in industrial areas or in urban areas, we have measurements that goes more or less around this curve. So the idea is to detrend it by passing a curve through the different station, and then we get this map of characterization of each site. We make the kriging, and then we get the final map by retrending, by adding again the concentration. Maybe it's a bit confused, but what you have to remember is that to make this detrending, we use a beta factor, which is a combination of the land use. So we can easily get from geographical maps where we know here we have urban fabric, here we have a lake, here we have anything. Well, there are 44 classes in the Corinne land cover maps, and each of these class, the n, is multiplied by a factor that somehow relate this class to an emission factor. So that's what is done in the Rio model, and in the PMLab model, the University of Aachen went one step further by including the actual emission from the EPRTR sources. It's a database at European level. So this terms takes into account the emission, and these terms take into account the land use. And why is the land use important? Because depending on the typical height you observed in the land use, the aerodynamic roughness will be different. So it will be easier or more difficult to disperse pollutants depending on the roughness. So this map is just the land use, as we can obtain it directly from the euPrevent website. And this is the emission map 5 by 5 kilometers that was produced by the EPRTR. So we combine both these information, and we can try to model the PM10. And this slide is just to show that if you see the red curve is the one that was determined with the PMLab model, and the blue one is the one determined by the Rio model. And you can see that we have a somewhat increased coefficient of determination. We go from 0.66 to 0.77 in terms of correlation. So that was a slight but interesting improvement. And this leads to the creation of the PMLab interface, also made by the University of Aachen. So, and it's still running. It was 13 years ago, but the code is still running fine. So you can see the shape of the Eurydium Rhine. And the points are the different stations, where if you click on them, you can get the PM10 concentration. And the colors, of course, indicate how polluted these sites are. And this is a good and a bad example at the same time, because this station had a problem, or at least the measurements were very, very high and probably not plausible. It was about 200 micrograms per cubic meter. So I doubt that there was really that high concentration. And you can see that it influences a large zone because there are not a lot of stations very close to that one. And the land use is pretty much homogeneous in this area. So that's why we had a large purple spot on this map. I checked the map yesterday and it was all green. Everything was fine again. Yeah, thank you. And also on this platform, you can see that there's a small tool that can determine where the air masses come from. That's something developed by the US Environmental Protection Agency. And you can just get the information. So you know that 48 hours ago, the air that's being in the center of the Euregio came from the South Atlantic, well, the Atlantic. Yeah, and that's it for the PM Lab platform. Now I will let my colleague Marie talk about the future.
Can you change my
Okay.
Good afternoon. So I'm going to present you one of our last project, the project WA, goes in English. The objective of this project was to improve our knowledge of exposure to outdoor and indoor pollution using measurement made by a citizen with portable device, notably the ISSeP local sensor system, and also with modeling with the atmospheric model at the city scale. And we will compare the value. So to begin, this is the evolution of the Belgian population exposure to PM2.5 concentration. The map is based on the Rio interpolation technique that Fabian just presented. So you can see that in 2016, the population were not exposed to concentration higher than 20 micrograms per cubic meter, but so no exceedances of the European limit of 25 micrograms per cubic meter, but 85% of the population were exposed to concentration higher than the old World Health Organization limit that was at the time 10 microgram, and now the limit is 5. So higher percentage of population were exposed to this concentration. So, but as I said, no, I didn't say that the WA project was to improve the exposure estimation in 2 cities in Belgium, Liège and Namur, but we will focus only in Liège today. So Liège, it's close to Ben and close from the border with Germany and Netherlands. Right. So to start, we can estimate the population exposure using the regional air quality network. So in Liège, there was until 2018 5 stations for the measurement of particulate matters. And since 2019, we have also a traffic station. So to estimate the population exposure, we attributed the value of the concentration from the closest station to each point of the territory, and we weighted the concentration by the population using data population at the 100 kilometers. And so you can see that for 2019, the exposure was around 8 micrograms per cubic meter for PM and 1 microgram per cubic meter for BC, so black carbon. But black carbon is not there is no recommendation for the concentration limit. So you can so this estimation, it's not really reflect the data, the condition where population live, and not the condition where the people are during their daily activity. So you can see here two situations: people living in a street canyon in the city center, and a house in the suburban area of Liège. So we can imagine that the concentration must be higher in the city center. But if we select the closest station, we can see that the closest station near the street canyon measure less concentration than the station near the suburban. So it's not a good estimation. So it's why we with in the project WA, we made a mobile measurement of concentration with 60 citizens in Liège from October 2018 to November 2019. And we give to the participant a set of mobile device with a measurement rate of 1 minute. So in the set, there was the low-cost sensor system developed by ISSeP, but there is also an etalometer for black carbon and a GPS to track the participant during their activity. So the measurement take place over 1 week, and we ask to the participant to complete activity and health logbook. So just a slide to present a little bit more the ISSeP low-cost sensor system. So it's a portable device, and we can have measurement at the resolution of 1 minute in this case, but we can go until the 1 second rate. So we can measure with this device different pollutant, gaseous pollutant, and particle pollutant. And we also have some meteorological variable. So it's just a slide to show that the measurement of particle meters made by this sensor fit quite well the value of reference station. But it's not the case of the gaseous pollutant. The gaseous pollutant needs some calibration to obtain good value. So here it's an example of daily activity of a participant, where we can, with the evolution of pollutant during the day, we can see the impact of notably the travel by car. We have peak in the concentration since the participant travel take his car. And here it's an extract of the report we sent to the participant. It's a table showing the exposure of each participant compared to the exposure of the group for the different activity they did. And here, if we look at the group, we can make some conclusion that it's not without surprise. We can see that you can click. We can see that
Where's the point?
Oh, it doesn't matter. We can see that the people spend most of their time inside, at home or at work, and in daily travel, with a concentration of 7 microgram, 4 and 6 microgram. But it's during the outdoor activity, like indoor leisure or indoor sport, that the concentration were the highest, with 9 microgram per cubic meter for indoor leisure, and also for the indoor sport. It's also during this activity that the maximum concentration were recorded, with notably 64, 90 for the indoor sport. it works now. And we also measure the black carbon, so it's the product of incomplete combustion. It's a good indicator of traffic, and you can see that it's during activity like picking up children or travel that the concentration were the highest. I show you the median value because when we make measurement like exposure measurement, the people are sometimes exposed directly to the source pollution. So we think that it was more robust to use the median, but we also show you the mean because the European or the World Health Organization compare their limit to mean value. So if we want to compare with official limit, we have normally to have to use the mean. So next slide. Regarding travel mean, you can see that it's the car and the walk that was the most used with yes, you can click. Yeah. So but it's for the bus and for the work that the people were the most exposed. And if we look at the black carbon, you can see that it's also during bus travel that the people were the more exposed. The mean again. So similarly to Sexton and Ryan, we try to estimate the daily exposure by weighting the different exposure during the different activity, weighted this exposure by the time spent for this different activity, and we can estimate the daily exposure to 6 microgram per cubic meter for daily indoor and outdoor activity. But if we look at the mean concentration, we have 18 for the indoor activity and 13 for the outdoor activity. So we also estimate the population exposure with the atmospheric model. It's a model developed by Vito in Belgium, and it's a model allowing the simulation of the concentration at the street level, notably with a module simulating the concentration dispersal in street canyon. And so just to show you the inputs we need, so we need the building to know the configuration of the street and notably identify the street canyon, but we also need the traffic on the network and the vehicle emission rate. And then you have a map of PM2.5 concentration, for example. And if we zoom in, we can see you can see the city center of Liège, and notably a very peak of concentration at the entrance of the Tunnel de Cointe, so the big tunnel in Liège. And we made the same exercise then for the regional air quality network. We estimate the population exposure from the simulation of the concentration using atmosphere, and we have 9 microgram per cubic meter for the PM and also 1 microgram per cubic meter for black carbon. And then we try to compare the simulation with atmosphere with the citizen measurement. So the large circle correspond to the atmospheric concentration at 10-meter resolution, and we aggregate the citizen measurement at the same resolution and also at 1 hour rate. And you can see the very fuzzy map. But if we zoom in, you have here only the measurement corresponding to travel activity to be comparable with the result of the model that simulate only the outdoor simulation in street. And you can see when we try to compare the two, that sensor, it will be that the pedestrian were more exposed to pollution than a car driver, but it's not the case for the model, but it's surely due to the fact that the model simulates outdoor simulation and not the indoor concentration, like the measurement in the inside of the car. And you can see that the error is very large for the pedestrian value, because pedestrian people don't always follow the road network for their déplacement. So the result, the comparison with model and sensor are less good. And here it's to show that the model and the measurement agree that that biker and walker are less exposed to black carbon than the bus commuter or the car driver. And we can see, you can also see that the correlation, it's also better when we analyze the mode using only the road network. The correlation is less good, as I said, for the PM 2.5. It's less good for the walker. So just a conclusion. So the different estimation indicate that population in Liège were not exposed to concentration higher than the European limit in this year. But if we look at the new limit or recommendation limit from the World Health Organization, the concentration are too high. This estimation are complementary. Regional network provide limited but reference measurement. Atmosphere provide high spatial resolution mapping of concentration, taking street configuration into account, like a street canyon, and mobile measurement provide the exposure of a dynamic population. We can follow the participant during their daily activity, and it's also difficult to compare these different sources of measurement. And the perspective, so we would like to focus on particular sites like street canyon or big boulevard, also make the analysis for nitrogen dioxide, exploit the new network of low-cost sensors we just installed in Liège. We also launched a new project called Mamba to focus a little bit more on indoor concentration. And we also have a project on outdoor and indoor transfer in the vehicles. Thank you.